sistema SAR de interferometría para monitorizar a través de la ocultación los movimientos de terreno. ¿De acuerdo?
Thank you. Muchas gracias. I've been told to speak English for this presentation. For you it's fine. If you do not understand, please feel free to interrupt me and I will explain in Italian, not in Spanish. I'm not able to go in Spanish, but I'll try to go very slowly. We have seen that one of the tools to reduce vulnerability is to monitor deformation. So this is a remote sensing technique that uses radar signal to monitor deformation on the ground. And we use this to monitor several kinds of processes, natural processes. The outline of this presentation, first of all, I'm going to explain a little bit of radar remote sensing. Then I'm going to go a little bit into detail, very simple, about the technique, the original technique. Then we will see some advanced technique, recently developed. And then at the end, I'm going to show you some of the application to cases of studies that we studied at our institute back in Italy. So, what is radar remote sensing? SAR is a technique that was developed at the beginning of 1990s, especially the space for radar interferometry, and was used at the beginning to measure Earth's topography, to create digital elevation model of the terrain, and to measure ground surface deformation. But what is a radar? Radar are active sensor. An active sensor is a sensor that provides its own illumination. It's not like a camera, like a photograph that you take. The camera exploit the light that you can see from the flash or the light coming from other sources. While radar uses their own energy to illuminate the scenario. So in this sense, there are active sensors. What they do is that they transmit the signal of electromagnetic energy, and then they measure, they record the backscatter radiation that comes from the target. Why the radar is so useful for example, for a lot of persons, but especially for us as a child scientist, is because it's weather independence and it's a 24-hour operation. What means? If you have satellite, optical satellite, towards the ground, the first thing that you see, you have to see clear sky, no clouds, because the light that we see or visible is not able to pass through clouds, for example. Here you see, this is the wavelength of the electromagnetic signal, and this is the atmospheric transmission. That means that here, all the energy that we send to these wavelengths can pass through the atmosphere 100%. You know, so you have this is a good frequency, and this is what use the microwave bands. For example, there are some other radiation that cannot penetrate the atmosphere. For example, the UV, you can see there are zero transmission of the atmosphere. So that's why radar signal can pass through clouds. So we are able, despite the visual, the optic, through the radar to see through clouds. And since we provide our own illumination, we don't need the sunlight. So we can acquire both night and day without any problem. This is one of the most one of the first satellites employed for radar remote sensing. These are two twin satellites, ERS-1 and ERS-2, were launched at the beginning of the 90s by the European Space Agency. What you see is that this is the antenna that we use to send the radar. This is an artistic sketch. And these are some parameters that it's, I mean, the only parameters really important to us is that the altitude is about 800 kilometers from the Earth's surface. And so, for example, they are very low on the ground surface. If you consider that the GPS satellites are 20,000 kilometers, okay, these are just 800 kilometers. And these are the repeat cycle. Repeat cycle means how often they can pass through the same area, okay? So 1, 3, and 35 days, that was the beginning. And the other thing that is important is the frequency that you use. This is important because this gives you the sensibility to the deformation you can measure. From a theoretical point of view, we can measure deformation up to half the wavelength that we use, so about 2.8 centimeters. Now I go to how it works with some basic terminology. So this is the antenna that is carried on the spacecraft. The spacecraft is going through a flight path, okay? So the trace on the ground, it's called azimuth direction, right? This antenna usually points sideways. Most of them are right hand. So when we point with an angle that we call look angle, okay, that is not vertical like some optical sensor, that we have some inclination. For ERS satellite, this inclination is 23 degrees, okay? And we have another direction. This is called the range direction. So as the spaceport travel through the flight path, send some pulse on the ground, and this pulse has a length that we call T, and this pulse illuminates an area on the ground. This area is called the footprint. Okay? Then we have this strip technique. That means that we can strip all this swap. To give you the dimension of what we can see, usually this swap is about 100 kilometers wide. Okay? While a single pulse can illuminate an area of about 5 kilometers. Then if we add all these pulses, we can have strips of about 100 kilometers for 100 kilometers as well. So we have these two directions are very important. The azimuth direction and the range direction, because along this plane is where the image is going to occur. Now I'll show you how it works. Why it is we call it synthetic aperture radar and not real aperture radar. Real aperture radar are the radar that you see, the one that are spinning off to detect airplane, for example. Those are real aperture radar. This synthetic aperture radar, they're called this way because just like more or less photogrammetry, I don't know if you know a little bit about photogrammetry, we are able to see the same point because the antenna, when we illuminate with the pulse, we have a cone, you know, and so at the beginning, let's see that the satellite passed by, and then we illuminate for the first time this object. Then the satellite moves here, another pulse come, another pulse come here, another pulse come here. At the end, when the satellite passes by, this is the last position where we can see the same point. If we can add up all the information about this point, we can create an antenna that is not just a 10 meters long antenna that we mounted on the satellite, but it's several hundred of meters. Why this is important? because of resolution. With a small antenna, we will see later, with a small antenna, we will have a very, very bad resolution on the ground, several kilometers. But if we can add up all these pulses where we see this object, and we can simulate a very large antenna with the processing, with some algorithm and processing, we can simulate an antenna that is about 100 of meters length, and then we can find a resolution that is few meters. Okay, this is on the azimuth, on the ground direction. This is talking about resolution, how it works. Okay, in a radar image, we have two resolutions. One is along the range direction, where we point in the radar, and the other one is about the azimuth resolution, the direction. So the pixel where the image is formed, they're rectangular. They don't have the same dimension because we have different resolution. Range resolution is strictly connected to the length of the pulse. Remember the pulse that we sent? If this pulse is very short, we have a better resolution. C is the speed of light, right? So it's a constant. So in order to have a better resolution, we have this quantity has to be smaller and smaller and smaller to have a better resolution, right? 1 meter is a better resolution than 10 meters, right? So we have to reduce this pulse, okay? But this pulse brings also the energy of the radar. So if we reduce way too much this pulse, we don't have the backscattering signal then. Okay, so there's a trade-off. We have to decide, in order to achieve the better resolution, the energy, the amount of energy. Let's say that for modern illumination system, this resolution can be up to 1 to 3 meters. So it's very accurate. Okay. The azimuth resolution, this is the pulse. You see the pulse, and these are the resolution cell, and these are the pixels, because you have to imagine a radar image like a series of pixels, each one has an information. Okay. Azimuth resolution, the resolution along the line of path of the satellite, is different if we use a real aperture radar or if we use a synthetic aperture radar. And this is a very weird relationship about things. First of all, because you see that if you use a real aperture radar, resolution is proportional to the range. The range is the distance between the sensor and the target. So if we go far away, the resolution is very poor. Okay? While in the synthetic aperture radar, we don't have VR. Okay? So azimuth resolution is independent of how far we are with the satellite. We can be 20,000 meters, we can be 1 millimeters, the resolution is still the same. This is very weird, but we can achieve this result with mathematical processing. The other thing is the position of the length of the antenna. This is the length of the antenna, which is the physical dimension of the antenna. Here you see that if the antenna is bigger, the better resolution that we have. While for the synthetic aperture radar, we need a very small antenna to have a better resolution. Okay. So as a matter of fact, with the synthetic aperture radar, we have a better resolution. If you think that more or less all the length, this is the wavelength that we employ. If you think that more or less the length of a spaceborne antenna is about 10 meters, we have a full resolution of about 5 meters in the estimate. The other thing that we have in SAR images are distortion. This distortion comes from the fact that we create the image over display. Okay, so we don't see the image from up above of the nadir angle like the optical image. we see some inclination here. So this is the plane of where the images is formed, and this is of course the topography. So we have several things that several deformations that we have to take account of, and the most important are these, for example, this foreshortening. If we have relief, okay, if we have some topography, that means that the slope that is facing the radar in the images appears shorter than it really is in the nature. Okay, just because when we form the image with the radar is a distance measurement device. So things that are closer are imaged before in what we see. So for example, just take a look here. So we signal arrived, okay, in layover that is we arrived here and we frame first of all the peak of the mountain that is formed, and then after the signal arrived and we form this base. So the base is here, and while the peak is here, which makes no sense from a topographical point of view, because from the topographical point of view, this is come first, and this is on the other side. So we have a displacement of the relief. Okay. This is how it looks like an amplitude image of the SAR image. This is Malta, okay, and Malta Island is a very small island. You can see sea all around. You can see some relief. This is the airport, appears dark, and then we will see why the airport appears dark, because every pixel carries an information about the amplitude and the phase of the scattered target that we got. Okay, amplitude is related on the nature of the target. Buildings reflect very well because we have a huge amount of radiation that is scattered back from buildings, vertical buildings, okay, metal things, poles, everything that is vertical can reflect very well because the signal is scattered back. So we have a very high amplitude and appears brighter. Okay, here is the city of Valletta. You see that this white spot, they are all buildings. Okay, while very smooth surface, okay, like roads, like calm water lakes, okay, they appear very dark and rather images because the signal is scattered back. So it's just a very small amount of radiation that comes back to the. So they appear very black. They appear very dark. That's why, because this is the landing of the airplane. There is a very flat surface that appears dark. The other information that we are mainly interested in is the phase, because when we will see the phase, gives us the information about how distant is the reflector from our sensor, and that is going to be the information that we will exploit to create the deformation maps. Okay. So interferometry is a technique, as I told you, that exploits the information contained in every pixel and concerning the phase. And if we are able to see from slightly different position the same object, we are able to reconstruct the age of the object on the ground and to obtain several other information. This is how it works in principle. V is the interferogram. R and A is the range and azimuth coordinates. So this is so you just think of an image like a mosaic of pixels. Okay? Each pixel has a coordinate. Every coordinate got some information that we call V. And how we create, if we can frame the same point from two different positions, okay, and then we put together this information, and we go through a mathematical process that we can subtract the phase of the same pixel of one image from the other, and we have this relationship, this phase. The phase contained in every pixel of our interferogram is proportional to this distance, which is the difference in distance between the two acquisitions. And from this, we can retrieve the age of the ground. That's how we build digital elevation model in a very simple way. But we are not interested in the age of the position. We are interested in deformation. So, what we have from an interferogram, and I'm trying to keep it very simple, okay? This is the phase of the interferogram. This is what we measure, okay? This is what we measure. This is the measurement. Is related to the topography, so the age of the point on the ground is related to deformation if there's any. Because let's say that we frame this object, and this object formed, and then we have the other acquisition that is not simultaneously. It's about one day after, 3 days after, 35 days after. We have an extra phase that we acquire from here that we don't have here because this object moved. Okay? So we are interested to have this information. Then we, of course, have some perturbancy coming from the atmosphere because at the time of the two acquisition, for example, clear sky or very cloudy, okay? Electromagnetic signal can see through clouds, but it has different kind of delay, okay, that are related to the content of humidity. Just like what it happened with the GPS signal, okay? They have problem with the atmosphere. Then we have some noise, and then we have other parameters that are concerning the fact that the Earth is not flat, but is curved, okay? So the point is, from this quantity, from the quantity that we measure, we are interested in deformation. How can we get rid of all this contribution and just isolate this information? Because if we can remove all this information that we are not interested from what we measure from satellite, framing the same object after 2 or 3 days, we can see if this object moved with an accuracy of few centimeters. What we do is that we try to get rid of this deformation. So this deformation, the topographic deformation, is related to the Earth's surface, right? So what we're going to do is to, when we see later on, is we try to have a digital deformation model of the ground. And then we want to remove this contribution from the ground. I'll show you right now with figures that are much more interesting. This is the island of Malta, and this is a digital elevation model of the island of Malta. This is more or less the same digital elevation model that is superimposed to the Google Earth images. You know, when you use the Google Earth, you see 8 elevation. They are based on this model, more or less. What we do is that we know the satellite position, and what we do from this face here, from this model here, we're going to create a synthetic and not real interferogram. Okay, we're going to give to the altitude according to the relation that I showed you. We're going to do the inverse process, a phase. Okay, we're going to create a synthetic interferogram. This interferogram has the advantage that is we made and contains just 8 deformation related to the topography. So we're going to use this interferogram, which is synthetic. This is the real interferogram. We're going to use this and we're going to subtract the topographic phase. Okay? So we're going to get rid of the topographic phase. And at the end, we're going to arrive to the differential interferogram. Now, the differential interferogram do not contain topographic, but does contain deformation, atmosphere, okay, and some other sources of noise. So the other step is to get rid of the other contribution. Differential interferometry cannot do this, okay? We cannot separate those contributions. Advanced technique really can, and I'll show you in a moment. These are insert limitations. We said that we can get rid of the receipt of the topographic contribution, but we can have some residuals because our digital elevation model can be not very accurate, so we can have some changes. We will have deformation, we will have atmosphere, we will have noise, we will have problem knowing the exact position of the satellite. So what we want is to get rid of these parameters. The other parameters, for example, noise. What causes noise? Noise is caused by the fact that if we frame the same area in two different periods, what might happen? For example, if we frame a city one day and then the next day, probably we're going to have more or less the same thing. But for example, if we frame a forest, okay, we frame a forest, what happened? Or a city, for example. We have what we call the correlation. The correlation raises by the fact that, for example, in the forest, the branches on the trees are moved by the wind, for example. Okay? So, and this influences the phase that we measure, okay? Because the point is not stable, okay? So we have a loss of coherence, we call. So everything that is not strictly fluid, okay, like grass, trees, water, lose of coherence, and this causes noise. Okay. For example, this is a map of coherence. This is a map of coherence created by two acquisitions with a temporal baseline of 35 days. That means that we have the first satellite that passed, then the other satellite passed after 35 days. And what we see is the map of coherence. One, the white, means perfect coherence. 0, the black, means totally loss of coherence. Okay? As you can see, C is completely bad. Okay? What is brighter are where the columns or where there is bare rock. Okay? Just rock with no grass, with no anything like that. Why this is important? Because we can measure deformation just in the bright areas. We cannot measure deformation in dark areas in a very simple way. You see what happened after 140 days? Very dark. That means that if we take images very, very far apart in the time, we have very, very, very poor cohesion. And this is a limitation of the classical SAR. We can get rid of this limitation using a technique that was developed by the University of Milan that is called the permanent scatterer techniques. These techniques analyze the phase of single backscatter in the resolution cell and using a long amount of images acquired 2 times. I don't think if it's simple, I don't think I'm going to be able to go into details, so we will skip this part. It's just to give you an idea. It's about how it works, because and then we will skip all the formula. They are not very interesting. I told you that a pixel is a resolution cell on the ground, right? It's about 5 meters, 3 meters. But what happens if we frame, for example, this table? Let's say this table is a resolution cell, and you have several scatterers here. Okay? All of them, the signal arrive, rebound, and all of them goes back into phase. Okay? So if this is grass or trees, the phase that we have is completely useless. I mean, we don't know, it's random. We don't know exactly because the signal rebound. But if in one cell we have a very, very strong scatterer, the signal, the phase that scatter back is mainly the phase of this backscatter. So we know information about these backscatters. So we do not perform the analysis on the resolution cell, but just on one scatter. But we must be able to find those scatterers. Usually buildings are those scatterers. I'm going to go all this through, but just to give you an idea, we use a huge amount of images, and we create differential interferogram. So, creating differential interferogram, we put together 2 images, okay? We measure the phase in every pixel. Then, differential means that we use a digital elevation model on the ground, and we get rid of the topography. So now we have just the atmosphere and the noise, okay, to take into account. The second thing, and then we look for permanent scatter. We analyze all these pixels to see if we can find this kind of scatters. They are very, very strong. They are very, very bright in the images. And then we go to a model. What we're going to do is it's a model. And we're going to estimate those parameters. Estimating those parameters, we will be able to measure the phase contribution related to the atmosphere to every single. And then we're going to get rid of that atmosphere, and we're going to stay with the formation that we have. This is the functional model. So this is the phase that we measure. Okay, we're going to model the topographic residual and the formation according to this formula. Okay, we'll not go into detail. Then we're going to have all this atmosphere, noise, and orbital residual. We're going to get rid of those. So what we're going to do is we're going to see what is the error between the quantity that we measure, that is this one, and the quantity that we model. Okay? We want this error to be as little as possible. Okay? Once we have this error, we can filter this phase because atmosphere, it's let's say, I don't know the experience that you have in signal processing, but let's say that atmosphere, it's random meaning, okay? So it's especially random. You don't know where a cloud, for example, is going to appear so today. So we have a special kind of filtering that we're going to give us a result that is the estimation of the phase contribution to the atmosphere. Then what we're going to do is we're going to put it here in the original interferogram. We're going to get rid of this, and then we're going to have the phase that we measure that will be related to the deformation. Now we go to the cases of study that we show. This is in Malta. We investigated the coastal landslide along the northwestern sector of Malta. This part, there's a lot of rock slides. Okay, lateral spreading rock slides, and there are here, but not here. And the reason why there are just above this line here, which is a fault, is because there are these landslides that are driven by structural setting. And I'll show you how. this is what you have in Malta, what you find in Malta. You have coralline limestone, which is the more recent formation. And then below you have blue clay, below Visorina limestone, and lower coralline limestone. What happened? What happened that this fault, there are extensional fault, displace the eighth of the surface, of course. So one part on the northwestern coast succeed. So what we have here is that this is the northern part. This is the upper coralline. So this is a very brittle formation, very rigid. And below here, you can see above the sea level the blue clays. They are very soft and tender. So what happened? Clays deform. The very brittle stuff on the top start to collapse. And these are the results. You see all these blocks? These blocks start with the fractures and then they slide over the clay. On the south, you don't have all this because what you see above the sea level is the lower coralline. So the lower part, because all the part on the top has been already washed away by erosion. So you don't have blue clays should be on the top, they're not there anymore since ages. So they don't have this poor bedrock that we have. So this does not collapse. We monitor this coastal landslide by means of GPS formations, GPS survey. And these are results of the displacement that we measure. This is the zero reading was in October 2006, and after 5 years, in November 2011, we have the displacement of this benchmark. Red arrow shows you the formation there in centimeters. This is 6.8 centimeters in this direction. Is this rock to collapse, sliding down? And the circle, blue circle, are the vertical deformation. Okay, so we can see here these blocks here. You can see a small fracture in the upper coralline formation. This block subside and then push the other block to slide over the coast. This is particularly important because these houses that you see here, this is a fun park in Malta. Children goes there because they have entertainment. So potentially this is a very risky situation. The formation are very slow because this is more or less 1 centimeter per year, so it's sharp. We made a permanent scatter analysis, a very interferometric analysis. These are the result after processing more than 50 satellite PRS images. The dot that you see are those permanent scatters. Okay? And they are color coded. That means that blue, light blue, that means all these scatters are stable. Okay? Yellowish are the velocity of the formation of the other scatters. You can see this yellowish means that there are blocks that are sliding. And we are able to assess this deformation if you take a look at the scale here, millimeters per year. So yellowish is about 5 millimeters per year. Okay. Please notice that the only component of deformation we are able to acquire are those on the line of sight of the satellite. Okay, so these are the deformation components. This is what we measure. Okay, that means that if we have a surface that is moving this way, we are not able to measure that deformation. The other thing we are not able to measure is that among two acquisitions, these blocks or this permanent scatter moves more than the half of the wavelength we use. Okay? So between two acquisitions, if we use PRS satellite that use a wavelength of about 5.6 centimeter, okay, we are able to detect deformation smaller than 2.8 centimeters. Longer deformation, bigger deformation, we are not able to measure. This is another example of application. This is what is a landslide. Is in the Dolomites, very close to the Tangia. And this is Cortina. It's very, very famous resort for skiing this summer and for tracking. I mean, it's very houses are very expensive. Here we have a landslide, several landslides, treating the city, and you see those yellowish blue. And then we have these arrows are GPS measurements that we make. Red arrows, this is the landslide that moves faster. You can see 10 centimeters per month. So very, very, very fast. The black arrows is very, very, very slow. And then we perform, these are the results. The red landslide is this one. You can see it's an earth flow. While, and these are the results, okay, of the buildings built, that were built over the landslide. We use the same technique with a different satellite, and the data are from 2004 till 2010. This is the Cortina. You can see yellowish means deformation, again, millimeter per year. Okay? What you can see, you can notice here, there you go, is you see that through the main channel, the one that goes to 10 centimeters per year, we don't have any PS, we don't have any information. We don't have any information because this line goes too fast. Okay, so we are not able to track it. Well, we have other information about the two other landslides. You know, they are much more smaller in speed, in terms of speed. Okay, and here, once again, we have a good agreement of what we map, that by means of GPS, and what we've seen from the satellite. Another case, here we use basic technique. We didn't use permanent scatter. We were interested, these were Dolomites too, we were interested to see this array created by the degradation of the permafrost, the layer of ice below the ground. So we want to know where these arrays were. And you see that this blue are the area above 2,000 meters. Okay, below 2,000 meters, the models say that I mean, probably there's no permafrost at all. Okay, so we were looking just for the area above, and what you see is that the red dots, okay, and all the other things are net landslide or disarray coming from photographic interpretation, field survey, other things. This is the area of possible and probable presence of permafrost that was made by the model, by the Swiss, I guess, right? So they are very small, these are, right? They're reddish compared to the other area. We want to investigate those to see if there were deformation. And this is a technique that doesn't use the permanent scatter, that just uses the SAR. And what you see, this is the marmolada, which is the highest peak on Dolomites. You see some fringes here. I don't know if they're very clear, but those fringes are these are MAC landslide or MAC deformation disarray. Those fringes are exactly where we mapped using other techniques those landslides. Other kind of deformation, subsidence due to mining. This is a work that we made in collaboration with the University of Gothenburg in Sweden, and this is the Kiruna mine. Kiruna mine is very famous. It's the largest iron mine in the world. Okay, and it's in Lapland, very, very north. And the problem of the Kiruna is that the iron ore is on a plane and its inclination when they first started to dig in was the beginning of the century. And over there is in the middle of nowhere, there's nothing over there. Okay? There's just this town, old town of mine. What they did not recognize is that they start building the town here, but the ore was tipping towards the town. So when they start digging under the town start to succeed. Okay. Now, since they have a lot of room, they're planning to move the entire city, which is 20,000 inhabitants, to another place. So the town itself will be abandoned, and they're going to build exactly the same replica of the town into another position. This is what we have seen from satellite, putting together two images, PRS images, coming from 1992 and 1993. We have 2080 days, and then we have this parameter. This parameter is called perpendicular baseline, which is the distance between the acquisition, the physical distance between the acquisition. One thing that I haven't go through the details is that if we can frame the same point very close, we have a very high sensitivity to deformation. And the topographic phase is not very important. We don't have the sensitivity to the 8, but much more. So if this parameter is very small, it helps a lot. It helps a lot. What we've seen here is, this is the mine, this is the town. You see all these fringes here? Maybe they are not here. That means that these are deformation going on. So to give a better idea of what we noticed here, this is a color-coded image of the deformation. The town of Kiruna, those are the banks, they're digging this way, okay? And what you see, it's now, it's greenish and yellowish, it's more or less stable, around 0. It's the blue and the deep purple is -3, -6 centimeters. Okay? There we try. Here, the formation of the line is very clear. But we made a deformation analysis using a permanent scatter. This is the city of Junio itself. Again, you see the yellowish, okay, part. And then you can see, for example, if we take this permanent scatter here, and this is the time scale, this is the deformation, okay. The cross here are the observation, what we measure from the satellite, you see? And the line is a very straight line, the model is the linear subsidence, 2 times that we measure. So we are able to estimate the deformation rate. Deformation rate, you see, it's almost 2 millimeters per year. Okay? So we are very accurate. But we wanted to know if we were sure about what we've seen. If you go to Kiruna website, you see a deformation properties. They made some geotechnical model, and they say that this is the town, and they say that in 2013, okay, according to the data that they acquired in 2007, deformation will reach this level of the town. Okay? Then when we start digging and digging, okay, deformation is going to move. Okay. But this point was the point that I showed you in the slide before. So we went there in Lapland. We look for that point with GPS position, and what we find cracks on buildings. Okay? But what was the trick is that we use images coming from 1992 till 1996. So those deformations were already recorded in 1996. This model said the deformation were at here in 2013. So we were able to demonstrate that the geotechnical model that they used was not accurate at all. Was was underestimating the real intensity and speed of the formation. The other thing, it's in Lapland, is a very interesting fault. This is a fault. You see, this is a picture taken from the helicopter. This is a post-glacial fault. This fault has 10,000 years. And this fault was generated in a single event by a huge earthquake. 8.7 estimated in the Richter magnitude, so a very strong earthquake. And this fault it's very famous because usually faults are in between plates, right, where the egg is. This fault is an intraplate fault, so it's in the intraplate. It's not in the margin of two plates. And this probably was caused when the very thick layer of ice covering Lapland was removed. Okay? So at a certain point, you have different kind of weight in Lapland, in this area. They're suffering of glacial isostatic adjustment. That means that those land that since 10,000 years ago were covered by a thick layer, 1 kilometer of ice, now they are not covered anymore and they're releasing, so they're uplifting. Okay? There's towns, Luleå is a town that is in the Baltic that is uplifting 1 centimeter per year. Okay? Crazy enough. Okay? So probably this earthquake and this fault was the result of this ice retreating, right? That create this elastic rebound. Well, we wanted to investigate if this fault was moving or not. Okay, still moving or not, because it's important with all the geophysical model. And you see, no buildings there, not a chance to apply permanent scattering interferometry. So we go to regular analysis. The problem with the regular analysis is that you might misinterpret the fringes, and you might think those fringes are deformation while they are just atmosphere, because we cannot get rid of those, right? So it's a quality control that we do. You put different interferons taken at different times, and you see if there are some fringes that are persistent in one position. If they are persistent in one position, it cannot be atmosphere that is totally random. It has to be deformation. And what we noticed here, just to give you an idea, those are images acquired 1992, 1996, 1999. There are different images, and you may see different kind of spot here, for example. There is not here, there is not here, but there is always one spot here, one spot here, and one spot here, very close to the fault. Moreover, we use different satellite. Okay? We just not use DRS satellite, we use MVSAT satellite, and we use different tracks, okay? Different position. And what we can still see, beside all the noise here, is that those fringes are still there. Okay? That means that has to be deformation. That means that the fault is still active, and this is the only technique that can lead to those faults. You cannot, those faults are 150 kilometers long. You cannot put instrumentation there. They're a very remote area, and in the winter time, there are about 3 meters layer of snow over there, and they are inaccessible for more or less 9 months per year. Those are other side effects of the earthquake and the fault, landslides. Those spots here are landslide. And there are very few mapped landslides. And actually, those landslides help a lot to reconstruct the structure of the fault and the origin of the fault. Because this land is not prone to landslide. The slopes here are very gentle, you know, the material is not clearly material, it's silt, so they're not prone to landslide. So what they think is that the earthquake and the shocking when the fault was generated create a landslide. Okay? And there was a debate, either the fault generated with the layer on, with the ice layer on, or after the retreat of ice. They were able to say that it was after the retreat of ice because they were able to see landslide. Otherwise, since these landslides are seismically inducted, if there were still the layer of ice on the top, probably the compression would not generate the landslide. Why? If the earthquake occurred when the ice retreated, that's when the landslide was formed. So this landslide helped to was one of the let's say one of the things that permitted to date back the fault. So it was very important. Those are other considerations about what we were able to see about, for example, the other thing that we can see about that fault is since that fault was moving, I mean, was thought that it was an inverse fault, you know, fault like would not a fault like a strike fault, okay? And we were able that the track of the satellite, it's more or less almost parallel to the length of the fault, to the direction of the fault. So if the movement was, we were not able to recognize it. The fact that we saw movement this way helped us to consider, to give us extra information. And all the other information from a quality point of view that you can retrieve. Thank you for your attention.
Mantovani nos ha presentado esta técnica para valorar con mucha precisión tanto movimientos en horizontal como en vertical y que de alguna manera pueden barrer un área muy importante sin la necesidad de tener equipos desplazados continuamente en el sitio, sino simplemente con lo que sería la respuesta de ese reflejo de onda electromagnética o del tipo que sea según el aparato y cómo es recibida en el emisor. ¿Vale? Bien, lo que vamos a hacer es pasar a un turno de preguntas. Si se os ocurre algo, se las hacemos en español o en inglés, como veáis, y terminar. ¿De acuerdo? Nos damos un momentito, nos vamos a hacer unas preguntas. ¿Any question? ¿Tiene alguna pregunta? Si queréis hacerlo en español, se lo intentamos traducir. ¿Alguna curiosidad, algo que os haya llamado la atención, algo que no hayáis entendido? ¿Algo que hayáis entendido?
Yo tengo una que en el tercer caso que hemos visto de estudio con el satélite hablaba de la montaña que se congelaba en la parte superior, ¿no? Que era de 2000 metros, era la estimación que teníamos de congelación de la montaña. ¿Por qué se estudia eso? ¿En qué puede afectarnos que se congele toda la parte de arriba de la montaña?
For the landslide. Because Christian said he's the geologist, but We wanted to, this was a European project, it's called Permanent, and we wanted to map if there were still a layer of permafrost on the Alps, and to see, because usually this permafrost lay under the ground. With global warming, this permafrost is of course melting and reducing, and this reduction create problem with the stability of the slopes. So it was important to see if there were still permafrost, where it was, because in the future that might create a problem to the stability of the slope.
Yes, the point is that when the permafrost melt, you have many water available for free circulation in the ground, at the surface, but also underground. And so, since the groundwater level is one of the main triggering factors of landslide, and so this is why it is important, because there's many structures on the highest peak of the Alps, like barracks or ski pistes or ski lifts and so on. So it's important to understand the effect of the permafrost melting in the deformation of the ground and on the structure that lies on the ground. This is why this European project try to investigate all the Alpine arc, with the German, French, Swiss people and Italian, in order to understand the effects of the permafrost melting due to climate change on the structure. Mainly ski lifts, touristic infrastructure mainly, but anyway it's very dangerous in terms of economic losses, because the reconstruction of the ski lift is very expensive. And so it's worth the
No sé si lo habéis entendido, pero hace falta que lo comente un poco, pero bueno, en principio vamos a hablar un poco de un proyecto europeo para intentar identificar todas esas zonas de máximo riesgo por permafrost, porque claro, el tema de la estabilidad, yo he hablado en muchas ocasiones también de la importancia que tiene el agua, cómo el agua desestabiliza o reduce la resistencia al golpe de los suelos, y un permafrost no es más que agua en estado de congelación, y esa alteración de ese permafrost es una alteración de esas propiedades, en esa tensión efectiva que hace que al final los parámetros resistentes del suelo varíen, ¿vale? Y los riesgos que ello conlleva, porque son zonas turísticas, zonas donde hay muchos riesgos por personas, por infraestructuras importantes. Normalmente además que cuando ese riesgo se produce cuando hay una gran aglomeración de gente, y bueno, ese es uno de los motivos. ¿Alguna cosa más que queráis comentar?
How much is the cost? Can you compare the cost of the SAR analysis compared with the traditional one in the same area?
La comparación, la relación entre el coste de las técnicas tradicionales de ocultación, de control, digamos, de deslizamiento, con referencia a la técnica SAR.
Radar images are very expensive. Especially the brand new images. Old images, like ERS satellite, dating back to the early 90s, they are very cheap. The point is that there's a trade-off. Comparing to the other technique, you might think that it's more expensive, but radar images can cover a big portion of the ground, so a bigger portion than any other technique. Yeah? And if you process all the images, you can have information about the deformation. Even you can link together 10 up to 20 years of informations. So you can have detailed information dating back from the 90s till up to now about the style of activity and the formation that we measure. So even if it's might look more expensive of that. Also the processing is very expensive. But you have much more information that so you have a better product.
It's more efficient.
Yeah, it's more efficient. You have a better product, but the cost. I mean, just to give you an example, a topographic station to measure the landslide. So one single landslide is a topographic station. It's about we spend about 60,000 euros.
It's special price. Yeah.
Special price, 60,000 euros, and just for one landslide. With the same amount, you can buy 30 images, 100 kilometers per 100 kilometers, and you are able to monitor more landslide and more things. Of course, there are some limitations on the technique. I mean, it's not always possible to find the right PS. It's not always possible to apply the technique, and if the movement is too fast, you're not able to track the movement. If the movement is along a direction that is not the line of sight, doesn't have a component on the line of sight of the subject, you're not able to estimate that. But in all the other cases is very effective.
Lo que nos viene a comentar un poco es que efectivamente el coste unitario del equipo es un coste muy elevado. Ahora, la producción de información que puede generar el equipo y hasta qué punto se puede extrapolar en una gran área y en un largo tiempo, en un largo periodo de tiempo, hace que los resultados, cuando se dividan por el beneficio que ello ocupa a muchas más personas, evidentemente, a muchas más áreas, pues son evidentemente, si se quisieran igualar con los equipos, más baratos que con la otra tecnología.
Anyway, it's important to stress that there's different target of the monitoring activity. I mean, you can monitor large areas, like in the case of the permafrost, or monitor a single landslide. So anyway, what I used to say is that it's really, really important to integrate different techniques in order to reach better results. Because otherwise, the risk is to lose many information. So if you integrate single point instrumentation or Earth observation techniques or aerial photographs, that it still remain one of the most used tools. But the better way is to integrate different techniques. Because even if one technique fails, you have other techniques that could support your investigation. Otherwise, if you center your activity on a single one, a single technique, the risk is that is losing many information.
Lo que viene a comentaros es que de alguna manera todas estas técnicas, la gran potencia que sostiene de ellas es cuando se usan en colaboración con otras técnicas. Lo hemos visto en clase cuando he hablado de las técnicas geofísicas, que son técnicas que funcionan muy bien siempre en colaboración con otras técnicas, digamos, directas, ¿no? Entonces ahí es donde realmente está el potencial para minimizar los riesgos y aprovechar al máximo la eficiencia de los equipos. A ver, ¿cuál es? ¿Otra pregunta? ¿Alguna otra cosita por llevar? Bueno, yo solamente agradecerles, thank you very much for your English, thank you very much. Decirle al profesor Mantovani que le agradecemos mucho el interés que siempre muestra por nuestra universidad, que aquí tiene su casa, estamos encantados de recibirle, así que bueno, como siempre agradecidos y hasta la siguiente.